let me just say something preliminary to begin with. I'm not sure, well, when I was asked to do this exercise session, I was not at all sure exactly what I should do. So this is my proposal, and I hope you're happy with this. So the idea is I will tell you a story which will involve a number of interesting strongly regular graphs and a number of other topics in various parts of discrete mathematics. And on the way, there will be a number of questions, which may be just proving things that I've said. Some are easy, some are hard. And so I put in this little tag, this question mark tag, to indicate things that you should try and prove. And there is a file containing the problems and the solutions. So if you're interested in getting that, please let me know. So anyway, this is what I propose to do. Okay, so shall we make a start? So to remind you from the last lecture, strongly regular graphs are one of the, I think, most important topics or key topics in algebraic graph theory. So a graph is strongly regular if it has, here are the four properties again, n vertices. Every vertex has k neighbors, so it's regular with valency k. And if you take two vertices v and w, they have lambda common neighbors if they're joined and mu common neighbors if they are not joined. So I'm going to be telling you the story of the strongly regular graphs containing no triangles, the triangle-free strongly regular graphs. Now, triangle-free means that if two vertices are joined, they have no common neighbors. So these are the strongly regular graphs with lambda equal to 0. Now, there is always one obvious example. If you take the complete bipartite graph, KNN, so the vertices come in two classes of size n, and you have all possible edges between the two classes. So if two vertices, there are no triangles because all the edges go between the two bipartite blocks. And if you have two vertices that are not joined, they will have precisely n common neighbors, the whole of the other block. So rather strangely, it turns out that apart from those rather trivial examples, there are only 7 known strongly regular graphs with no triangles. This has not been proved, but they've all been known for quite a long time now, and nobody has found another. So the really big question is this all? But I'm going to describe these graphs to you, and along the way, we will meet quite a few interesting pieces of discrete mathematics that have a bearing on this. So here are the 7 graphs. First of all, the 5 cycle, C5. That's strongly regular with these parameters, 5, 2, 0, 1. No triangles. And if two vertices are not adjacent, they have just one common neighbor. The Peterson graph, which we saw in the last lecture, it's on the web page for the graph theory course. If you look at the top of the web page on the right, you'll see the Klebsch graph. The Hoffman-Singleton graph, the Gewurz graph, a graph which doesn't have a standard name. I will call it the 77 graph because it has 77 vertices, and the Higman-Sims graph, which has an interesting story because it was actually found by Mesner more than 10 years before Higman and Sims, but somehow his work wasn't recognized. So you might think, I've got the 5 cycle, why don't I have the 4 cycle? Well, I don't have the 4 cycle because it's the complete bipartite graph on 2 and 2 vertices, so it's one of the ones that I've excluded. Okay, so I'm going to tell you the story of these graphs with problems along the way, and as I say, you are very welcome to try these problems, and if you want to write to me for a sheet with the problems and solutions, please do so. So the 5 cycle really needs no introduction. Peterson graph we've seen before. Here are those 2 pictures of it that I showed in the last lecture, one showing 5-fold symmetry, the other showing 3-fold symmetry. And here's another description of it. You take the vertices of the Peterson graph to be all the 2-element subsets of a set of size 5. So take the set 1, 2, 3, 4, 5, and take the 5, choose 2, which is 10 2-element subsets. Join 2 vertices if the subsets are disjoint. And so in order to prove that these are the same graph, what you might do is take each of these 2 graphs and label the vertices with the 2-element subsets of a set of size 5. So if I start off and I put the set 1, 2 there, then these 3 vertices have to be disjoint. So I can put 3, 4, 3, 5, and 4, 5. And then you have to fill in the rest of the picture and show that you can do that consistently, and the same for the other one. And once you've done that, that will prove that those 2 things are the same.
Hi, hello.
Yes, hello.
Yes, I just wanted to add one thing. Aren't these graphs called, they have a special name, the way you are generating these graphs, they are called, I can't pronounce them, I can just write them in the chat, but they are called Nessel graphs, if I'm not wrong, right? Nessel graphs.
Yes, indeed. But
Yeah,
they're a special case. I mean, this is the Kneser graph 5, 2.
Yeah.
And have any n and any k less than or equal to n over 2, and there's a Kneser graph. But the Peterson graph is so special. Whatever kind of graph theory you do, you will meet the Peterson graph quite early on, because it's you have, if you make a conjecture about graphs, try it out on the Peterson graph first, and if it survives that, then maybe it's true. It's a very important graph in its own right, and the other Kneser graphs are not strongly regular, so this is why I'm sticking to this one here. But you're quite right, it's one of an infinite family. Okay, so the next one on the list was the Klebsch graph. So first of all, here's a definition of the n cube. The vertices are all the subsets of the set 1, 2 up to n. So the 2 to the n subset. So this is a graph with 2 to the n vertices. You join 2 vertices A and B. These are subsets of 1 up to n. If their symmetric difference has size 1, that means they differ by just one element. So either B is A with a new element put in, or A is B with a new element put in. So that gives you a graph of valency n, because you can take any x, it'll, if it's in A, you take it out. If it's not in A, you put it in to get the corresponding neighbor. So this is a regular graph. Diameter is n, because you can only move one step at a time. So to get from the empty set to the whole of 1 up to n will take n steps. It's also an antipodal graph. That is, for every vertex, there's a unique vertex at maximum distance from it, namely the complementary subset. So yeah. Question?
Yeah, I'm sorry for interrupting again. I have a small confusion. The confusion is that you have used capital A and capital B to denote vertices, and I'm not sure that the vertices are also representing sets. Can that be just a little bit?
Yes, yeah. I've said the vertices are the subsets of the set 1 up to n.
Oh, yeah. So, sorry, I missed that. Thank you.
Yeah. Okay, so that's how it works. Okay, you happy? Good. Okay, so now, having got the definition of the n cube, here are 2 graphs that we can build from it. First of all, take the 5 cube. This is a graph of diameter 5, and it has antipodal vertices. For each vertex, there's a unique vertex at distance 5 from it. Now, I'm just simply going to identify those. So make a new graph whose vertices are the antipodal pairs in the 5 cube. And but if you have 2 adjacent vertices, then their antipodal pairs will also be adjacent. So there's a natural way of defining an adjacency rule. So this will give us half as many vertices, so 16 rather than 32, and the graph will have valency 5. And here's another one. Take the 4 cube. This is a graph on 16 vertices with valency 4, but now I put in extra edges. I take the antipodal pairs in this graph and I join them by edges. So each vertex is joined just to its 4 neighbors in the original cube and to the antipodal vertex. It turns out you can show these 2 graphs are actually isomorphic, and this is the Klebsch graph. It's strongly regular with these parameters, 16, 5, 0, 2, no triangles. And if you look at the Klebsch graph, take either of these definitions and look at the vertices at distance 2 from a given vertex, and you will find a copy of the Peterson graph. So there are some things that you might try to prove about this graph. And as I said, you've seen it before because there it is. It sits on the top of the web page for this graph theory course. Rather beautiful graph. So now a little bit about the spectral theory of strongly regular graphs. Suppose you have a strongly regular graph with parameters nk, lambda, and mu. You take its adjacency matrix to be A. We saw that in the last lecture. Let I be the... Gosh, I've got these the wrong way around. I'm sorry. J is the all-one matrix, and I is the identity matrix. I'm sorry about that glitch. I is the identity, J is the all-one matrix. Now, the adjacency matrix of the complementary graph, you take the matrix with all ones, you take the ones off the diagonal, and you take away the ones in the positions where their vertices are adjacent in A. This leaves the pairs where the vertices are not adjacent in A, so it gives you the complementary graph. And now, what equations do these matrices satisfy? Well, A times J is K times J, because if you take the matrix A, multiply it by the all-one matrix, you just go along a row of A and count the number of ones that you see, but that's the valency of the vertex indexing that row, so that will be K, because all the vertices have to be K. So AJ is equal to K times J, and A squared, now what does this count? This counts where you can get by taking 2 steps. Oh, and there's another typo, I'm sorry. It's Ki plus lambda A plus mu B. So that second equals there should be a plus. So that's because if you start at a vertex, one way of taking 2 steps is just to go out along any of the K edges and come back along the same edge, and that'll bring you to the vertex you started off with. So that'll give you a K on the diagonal. Now, if you take 2 adjacent vertices, they have lambda common neighbors. So there are lambda ways of taking 2 steps between them. And for non-adjacent vertices, that number is mu. And if you take those 2 equations, the first one tells you that the all-one vector J is an eigenvector with eigenvalue K. And because the matrix is symmetric, if it fixes a vector, it fixes the space orthogonal to that vector. And the space orthogonal to J is the set of vectors with coordinates sum 0. So that's an n-1 dimensional space. And on that space, J becomes 0. And so we just have a quadratic equation for A. So that gives you, that means it has just 2 eigenvalues on the space perpendicular to J. And conversely, if you have a graph whose adjacency matrix has the all-one vector as an eigenvector, and just 2 eigenvalues on the space orthogonal to the all-one vector, then it's a strongly regular graph. So that's something that you could try and prove. So that's how we can recognize strongly regular graphs from their spectra. And it can be shown, and this is also something that you might like to try, the Peterson graph and the Klebsch graph are the unique strongly regular graphs having those parameters, the parameters that we saw earlier. So to put it another way, in terms of spectra, if you have a graph with the same spectrum as the Peterson graph, which is 3, 1, minus 2 are the eigenvalues with multiplicities 1, 5, and 4, then that graph is necessarily isomorphic to the Peterson graph, because by what we said on the last slide, it's strongly regular, and then we're using the uniqueness of the Peterson graph as a strongly regular graph with those parameters. And the same works for Klebsch. If you have the eigenvalues 5, 1, and minus 3 with multiplicities 1, 10, and 5, it's isomorphic to the Klebsch graph. And we're going to use that to look at a nice problem that goes back to Alan Schwenk. So this is the problem. Schwenk observed that the Peterson graph has 15 edges, which is 1/3 of the number of edges in the complete graph on 10 vertices, which has 10 choose 2 or 45 edges. So Schwenk asked, can you partition the edge set of K10 into 3 copies of the Peterson graph? Well, on the face of it, it looks like you might be able to, but in fact you can't. And there's a very beautiful argument for that. Suppose that we have such a partition. Suppose A1, A2, and A3 are the adjacency matrices of the 3 Peterson graphs. So when you add them together, you get everything off the diagonal. So you get J minus I, the all-one matrix minus the identity. Now, remember what we said about all of these 3 have the all-one vector as an eigenvector with eigenvalue 3. So they all preserve the 9-dimensional space perpendicular to the all-one vector. So that 9-dimensional space contains the 5-dimensional eigenspace for A1 with eigenvalue 1. If we go back to here, 1 is an eigenvalue with multiplicity 5. So we have a 5-dimensional space of eigenvectors of A1 and a 5-dimensional space of eigenvectors of A2, in each case with eigenvalue 1. And 5 plus 5 is bigger than 9, so those 2 spaces must have a non-zero intersection. In other words, there's a space of dimension at least 1 on which A1 has eigenvalue 1, A2 has eigenvalue 1, J has eigenvalue 0, so A3 from this equation has eigenvalue 0, minus 1, minus 1, minus 1, or minus 3. Well, if it has eigenvalue minus 3, it can't be the adjacency matrix of the Peterson graph because its eigenvalues are plus 1 and minus 2. So it's not possible for A3 to be an adjacency matrix of a Peterson graph. So you can't partition the edges into 3 Peterson graphs. But in fact, this A3 is a graph of valency 3 and has an eigenvalue minus 3. And there's a result in about eigenvalues that says that if that happens, then the graph must be bipartite. And so if you could find 2 disjoint Peterson graphs in K10, then the edges left over would have to form a bipartite graph. And that does exist. So my next problem is find a partition. Partition the edge set of the complete graph into 3 graphs, 2 copies of the Peterson graph, and then one that's left over must be bipartite. Check that it's bipartite. Okay. But now we've done that for Peterson. What about Klebsch? The Klebsch graph has valency 5 inside K16. So it has 40 edges. K16 has 120. So once again, it seems possible on the face of it that the edges of K16 can be partitioned into 3 Klebsch graphs. Or can they? Let's try the same trick. So we have A1 plus A2 plus A3 is J minus I. And so again, really, we only assumed that the first 2 were the graph that we know about. So let's assume that A1 and A2 are adjacency matrices of Klebsch graphs. Then they have 10-dimensional eigenspaces with eigenvalue 1. And these 10-dimensional spaces inside a 15-dimensional space must intersect in at least a 5-dimensional space by the dimension formula. So the intersection has dimension at least 5. And on that intersection, we have eigenvalue -3 as before. But now you see we've got this -3 with multiplicity at least 5, and the valency is 5. From that, it's possible, using Cauchy's inequality, which again I invite you to try, to show that the other 10 eigenvalues are all equal to 1. So A3 is the adjacency matrix of a graph with 10 eigenvalues 1 and 5 eigenvalues -3. So it's another Klebsch graph. So unlike the Peterson case, in this case, if we partition the edges into 3 subgraphs and the first 2 are Klebsch graphs, then the third will also be a Klebsch graph. So in other words, we only have to find the first 2 and the third one's guaranteed. Can we do that? Well, yes. And here's a nice algebraic construction using the finite field of order 16. So the multiplicative group of this finite field has order 15. So it contains 5 fifth roots of unity. And that subgroup of order 5 will have 3 cosets inside the multiplicative group. So the set of fifth roots and of the 3 non-zero elements in the subfield of order 4, in fact. So we have 3 sets A, B, and C. Now, we're going to form the Cayley graphs of the additive group of the field with respect to these 3 subsets A, B, and C. And now, again, I leave the details to you as an exercise, but if you do that, you will find that all 3 Cayley graphs are isomorphic to the Klebsch graph. So in this way, we've actually achieved a partition into 3 Klebsch graphs. And while we're on that, they are all isomorphic because multiplying by a cube root of unity, the cube roots of unity are complementary to the fifth roots of unity. So multiplying by a cube root of unity permutes these 3 cyclically, and so they are all isomorphic. And this has a famous application to Ramsey's theorem. So I'll just briefly describe this. If you take the complete graph on 6 vertices and color the edges red and blue, then you must have a monochromatic triangle. There must be either 3 red edges forming a triangle or 3 blue edges forming a triangle. So this is a standard piece of discrete mathematics, and I hope you've all seen it at some point. And 6 is best possible because if you take C5, its complement is also C5. So if you take C5 and color its edges red, and you color the complementary edges blue, there will be no monochromatic triangles because the edges of each color form a C5. So 6 is the smallest number for which this statement is true. So what if you have 3 colors? Well, you can show, and I invite you to do so, that in K17, if you color the edges with 3 colors, you must form a monochromatic triangle. And what we're going to show is that 17 is best possible. And the reason for that is we've just partitioned the edges of K16 into 3 Klebsch graphs. So if you color the edges of the first one red, the second one green, and the third one blue, then we get no monochromatic triangle because no Klebsch graph contains a triangle. So 17 is best possible for that Ramsey number. So this argument goes back to Greenwood and Gleason. Okay, so let me press on. Another place where this comes up is in Moore graphs of diameter 2. So a Moore graph of diameter d and valency k is a regular graph, has valency k, has diameter d, and the girth is as large as possible, namely 2k plus 1. You see, if you have a graph of diameter d and valency k, you can start off from a vertex. You can move away d steps from that vertex. I'm sorry, that should be 2d plus 1. You can move away d steps. You can't get further away, so the next step at best will take you to another vertex d steps away from the first one, and then there'll be a path of length d going back, and that will create a cycle of length 2d plus 1. So a Moore graph is the one that achieves that bound for the girth. And in the case d equals 2, you see, we start off from a vertex, there are k neighbors, each has k minus 1 further neighbors, and we want no overlap among those. And that gives us k squared plus 1 vertices altogether. And so a Moore graph of diameter 2, valency k has k squared plus 1 vertices. And it's a strongly regular graph with these parameters. So we can compute the eigenvalues, we can compute their multiplicities. Those multiplicities must be non-negative integers. And from that, you find that k must take one of the values 2, 3, 7, or 57. Now, for k equals 2, there's a unique graph, namely the cycle, 5 cycle. For k equals 3, there's a unique graph, namely the Peterson graph. This result was first proved by Hoffman and Singleton, and they constructed and showed unique a Moore graph with valency 7. I'm going to give you the construction because it's rather pretty. And we still don't know whether there's a Moore graph of valency 57. It's been claimed, a non-existence proof has been claimed, but it's not generally accepted yet. So if you ask for Moore graphs of larger diameter, Banai and Ito and independently Damerel showed that the only possible graph is the cycle. So to construct the Hoffman-Singleton graph, we use the outer automorphism of the symmetric group S6, and this goes back to Sylvester in the 19th century. The symmetric group S6 has an outer automorphism, which means a group automorphism not induced by conjugation by a group element. It's the only symmetric group, finite or infinite, that has an outer automorphism. So it's a rather remarkable situation. So this is a brief account of Sylvester's construction, and please go through and check the details if you're interested. Take a set of size 6 and look at the complete graph on A that has 6 choose 2 or 15 edges. It has 15 one factors. One factor is a complete perfect matching, a set of 3 edges, pairwise disjoint and partitioning the vertex set. And it has just 6 one factorizations. These are sets of 5 one factors. See, one factor has 3 edges. So in principle, we could partition all 15 edges into 5 one factors. Well, there's a unique way of doing that up to isomorphism, but that gives us exactly 6 different one factorizations. So we start with a set of size 6 and find that it has 6 one factorizations. And let B be that set of one factorizations. And if you now start with B, that's a set of size 6. If you reverse the process, turns out you get back to A, because you can show that 2 one factorizations share a unique common one factor. So the one factors are like edges of the complete graph on B. And similarly, edges on A correspond to one factors on B. Points of A correspond to one factorizations on B. So doing the process twice takes us back to where we started. And now this is an outer automorphism, because if you take a permutation of A, it will permute the elements of B, and composing permutations of A will compose the corresponding permutations of B. So we get an isomorphism from the symmetric group on A to the symmetric group on B. And this is an automorphism of S6, which is not an inner automorphism, because fixing a point and fixing a one factor are completely different things. And the stabilizer of a point doesn't fix a one factor or one factorization, or vice versa. So Sylvester had marvelous notation for these. He called edges duads, one factors synthemes, and one factorization synthematic totals. Now, we're going to use this setup to construct a graph, and I think it was Norman Biggs who first constructed this graph. He called it the Sylvester graph. So we start off with that setup. We've got a set of size 6, and we've got 6 one factorizations. And this is how we build a graph. The vertex set is A cross B. In other words, it's a set of pairs consisting of a point of the set A and a one factorization of the complete graph on A. Now, when do I join a pair AB to a pair A dashed B dashed? Well, I look at A dash. Those are 2 points of the set capital A. So that's an edge. And we also saw that the one factorizations, B and B prime, have a unique one factor in common. If that edge belongs to the unique one factor in common between B and B primed, then we join AB to A prime, B primed. And that's the Sylvester graph. What is it? It's a graph on 36 vertices, has valency 5, and if you look at a vertex and its 5 neighbors, that's 6 vertices. They all lie in different rows and they all lie in different columns of the array A cross B. And if 2 vertices do lie in different rows or different columns, then either they're joined or they have distance 2 in the graph, or there's another vertex joined to both of them. Vertices in the same row or in the same column have distance 3. So that gives a rather nice graph. But this is how we go from that to the Hoffman-Singleton graph. Well, before I do, as I said, the number 6 is very special because this is the only symmetric group that has an outer automorphism. And that outer automorphism enables you to construct many other interesting combinatorial objects. But another special thing about 6 is that it's the only number greater than 2 for which there do not exist orthogonal Latin squares. So this is this was conjectured by Euler, and he made a more general conjecture which turned out to be false, but he was right about 6. It was proved at the end of the 19th century that there are no 2 orthogonal Latin squares of order 6. And now orthogonal Latin squares are used in experimental design, especially in agricultural research, to construct certain block designs called square lattice designs. This goes back to the work of Fisher and Yates at Rothamsted. So if you have n-squared treatments, then perhaps a square lattice design is a good way to lay out your experiment. But of course, if n is equal to 6, there are no orthogonal Latin squares of order n. So you can't do that. So what do you do instead? Well, it turns out that you can build something which is almost as good as a square lattice design using the outer automorphism of S6, using the Sylvester graph. And so this is Emlyn Williams. You can construct graphs which are almost as good as the non-existent square lattice designs. Anyway, the Hoffman-Singleton graph, here it is. This is how you build it. You take 2 symbols alpha and beta, and the set A and the set B and the set A cross B. These are the things that we had in the discussion above. So A is a set of 6 vertices of a complete graph. B is the set of 6 one-factorizations of that complete graph. And these are the edges. We join alpha and beta by an edge. We join alpha to all the points in A. So now alpha has valency 7 because it's joined to beta and it's joined to 6 points in A. And similarly, beta we join to the 6 points in B. We join A to all the pairs that form A comma B, and also B to all the pairs A comma B. And that gives A valency 7 because A is joined to alpha, and it's also joined to AB for the 6 possible values of B. And finally, we put in all the edges of the Sylvester graph that we've already constructed on the vertex set A cross B. And if you do that, you find that the resulting graph is strongly regular, and it's a Moore graph. It has 50 vertices, valency 7, no triangles, 2 points at distance 4 have a unique common neighbor, so no 4 cycles either. So the girth is 5. So that's the Hoffman-Singleton graph. And I talked about partitioning the complete graph into Peterson or Klebsch graph. Well, the Hoffman-Singleton graph has valency 7, so it has 1/7 of all the edges of K50. Can K50 be partitioned into 7 Hoffman-Singleton graphs? This has not been definitively resolved yet. No such partition is known. Martin Maciej reported in a conference that there are at least 1,600 ways of finding 6 disjoint copies of Hoffman-Singleton. So the edge sets are disjoint, and that will leave over a regular graph of valency 7. And in none of these cases did you actually get the 7th one also being Hoffman-Singleton. But it wasn't a complete analysis because they assumed that the set of graphs was invariant under a non-trivial group. And so there's still the case where there are no automorphisms. So that's a problem which is not yet resolved. Okay, so now I'm going to work towards the last 3 graphs. And let me start off with orthogonal Latin squares. Well, we constructed, in my lecture earlier on today, I constructed strongly regular graphs from Latin squares. Now I'm going to do something similar, but suppose we have 2 Latin squares of the same order. I'm going to say that these 2 Latin squares are orthogonal if whenever you take a letter from the alphabet of L1 and a letter from the alphabet of L2, so there are n squared such pairs of letters, then you will find a unique cell in which the L1 has the entry A and L2 has the entry B. So here's a little example. Here's a Latin square with the alphabet ABC. Here's a Latin square with the alphabet PQR. And if I just superimpose them, you see all combinations of an ABC with a PQR occur exactly once. So that's an example. And if you have a set of Latin squares, you say that they're mutually orthogonal if any 2 of them are orthogonal. And it's not so hard to prove, you can try it, that you can have at most n-1 mutually orthogonal Latin squares of order n. Now, if you have s-2, let's say for some number s, mutually orthogonal Latin squares of order n, we can follow the construction of the Latin square graph. So we take the n squared cells to be the vertices. We join 2 cells if they lie in the same row or in the same column, or if they have the same entry in one of the squares, one of the s-2 squares. I'll use s-2 here because it makes the formula slightly nicer. So this graph is strongly regular, and here are the parameters: n squared, s times n-1, s squared minus 3s plus n, and s times s-1. So that is something you could try and prove. When s equals 3, you have just 1 Latin square, and so that will give you the parameters for the Latin square graph. But anyway, so that gives you a strongly regular graph. And if you have a graph with those parameters, you call it a pseudo-Latin square graph. So it may or may not actually come from a set of mutually orthogonal Latin squares, but you'll call it a pseudo-Latin square graph if the parameters look like the parameters of a Latin square graph. And back in the 1960s, Bruck proved that if S is small enough compared to n, roughly the fourth root of n, if you have a pseudo-Latin square graph, so with these parameters, then it actually does come from a set of mutually orthogonal Latin squares. So those are pseudo-Latin square graphs. Now, Dale Mesner wrote his PhD thesis in 1956, and he had the lovely idea that if you take these formulae and you replace n by minus n and s by minus s, you'll get some numbers which look like the parameters of a strongly regular graph. So he called that a negative Latin square graph because we've simply taken the parameters and replaced n and s by their negatives. So these are the parameters of a negative Latin square graph. We don't know connection with Latin squares anymore. We don't ask that. We just ask that the parameters look like that. And if you look at the value of lambda, you see it's s squared plus 3s minus n. That's certainly greater than or equal to 0 because it counts something. So n has to be less than or equal to s times s plus 3. And moreover, if equality holds, then this number is 0 and you have a strongly regular graph with no triangles. So that's what Mesner did. And in fact, if you put s equals 1, then n will be 4, so n squared will be 16, and you get the parameters of the Clebsch graph. If you put s equal to 2, you get the parameters 100, 22, 0, 6. So Mesner in his thesis actually constructed a graph with those parameters, and a few years later he worked a bit harder on it and was able to show that in fact there is a unique strongly regular graph with those parameters. So the one he constructed is the only one. So that's another strongly regular graph with no triangles. Then what happened? Well, in 1967, Donald Higman and Charles Sims were at a group theory conference in Oxford. That was the year before I arrived in Oxford, so I missed this occasion. So at the conference that day, Marshall Hall had just announced the construction of a new sporadic simple group. This was Yanko's second group, J2. He constructed it as a permutation group on 100 points. Actually, he constructed a pseudo-Latin square graph with these parameters 100, 36, 14, 12, and found that its automorphism group had a subgroup of index 2, which was the Yanko group. So Higman and Sims were sitting next to one another at the conference dinner, and they started wondering whether there might possibly be another sporadic group acting as a permutation group on 100 points. Now, this just sounds like fantasy, but by the end of the evening, they had found one. This was the quickest construction ever of a sporadic finite simple group, no doubt about it. They constructed it between the conference dinner and bedtime on that day. So how did they construct it? Well, they knew that there was a particular configuration, a design with 22 points and 77 blocks, first constructed in 1931 by Carmichael and proved unique by Witt in 1938. So it's a Steiner system, S3622. That means there are 22 points. Each block is a set of 6 points, and any 3 points lie in a unique block. And Witt showed that the automorphism group of this Steiner system contains the Mathieu group, one of the earlier sporadic simple groups, M22, as a subgroup of index 2. So Higman and Sims said, right, we'll take Witt's design and we'll build the graph from it. So the vertex set of the graph are the 22 points, the 77 blocks, and one additional point, which I'll call star. That makes 100 points altogether. So we've got a graph on 100 vertices. What are the joining rules? Star is joined to all the points, all the 22 points. A point is joined to a block if the point lies in the block, so if the incidence holds. So that gives you the joins between the 22 points and the 77 blocks. There are no joins among the points, because if there were, that would create a triangle, and we don't want that. But when are two blocks joined? Two blocks are joined if and only if, as sets of size 6, they're disjoint, right? And they showed, well, it's fairly easy, that given any block, there are exactly 16 blocks disjoint from it. So it's joined to the 16 blocks disjoint from it, and the 6 points incident with it, and that makes 22. And you can show like this that the graph really has valency 22, and you can show that it's strongly regular. And using properties of the Steiner system, they were able to show that it was strongly regular with those parameters. And now they wanted to find the automorphism group. So they know that the automorphism group contains the automorphism group of this design, that is, contains a subgroup M22. So what they have to show is that if I start at a different point, if I replace star by a different point and look from that point, everything will look exactly the same. I will have another copy of the VIT design, which is unique, with the same joining rules. And they were able to do that fairly easily, and that showed that the automorphism group was transitive, and that it contains a new sporadic group as a subgroup, and that's the Higman-Sims group. Well, it turns out their graph, since Mesner had shown his graph was unique, it must be the same graph that Mesner constructed. So why did Higman and Sims get the credit for this and not Mesner? Well, there are various reasons for that. Mesner didn't know about this Carmichael-Witt design, and he didn't really understand groups either, so he couldn't use group theory to help him. He had to do everything with his bare hands. And also, he was a statistician, and even though this had arisen in statistical design theory, statisticians weren't terribly much interested in this particular object. But anyway, the group is certainly correctly called the Higman-Sims group. It might be better to call the graph the Mesner graph. And there's a nice paper by Misha Klin and Andrew Voldar, which you can find on this website, a long discussion of the history of Mesner and Higman and Sims and what actually happened. So I recommend that to you if you're interested in the history of these things. And okay, so there are two more graphs. We have the 77 graph and the graph on 56. So the 77 graph, well, you can probably imagine that, because in Higman-Sims construction, there were 77 blocks of the design, and we built a graph there by joining blocks of their disjoint, and that is exactly the one. So the blocks of the Steiner system joined of their disjoint, and there are its parameters. It can't contain any triangles because it's a subgraph of the Higman-Sims graph, which itself contains no triangles. And the 56 graph, you do a similar thing, except that you, instead of taking the vertices not adjacent to a given vertex, you take an edge and you take the vertices not adjacent to either end of that edge. And that gives you a strongly regular graph with those parameters. And that is it. Those are, as far as we know, all of the triangle-free strongly regular graphs. But you might like to take these definitions and prove that they are indeed strongly regular graphs. I'll give you a little hint for that. Before I do, just you can take the Mesner graph, or Higman-Sims graph if you prefer, partition the vertices into two subsets of size 50, such that the induced graph on each subset is the Hoffman-Singleton graph. This is not the sort of partition problem we were describing before, but still it's an interesting observation. Anyway, how to prove that these graphs are strongly regular? Well, use a little bit of design theory. A 2 design has points and blocks. Each block is a K subset of points, and 2 points lie in precisely lambda blocks. And it's called quasi-symmetric if there are just 2 different numbers for the size of intersection of 2 blocks. Any 2 blocks intersect in either A or B points. Now you pick one of those numbers, it doesn't matter which, and then the block graph of the design, as the block says vertices, 2 blocks are joined if they intersect in B points. So in the case of the 77 graph, we took the VIT design on 22 points and did this construction with blocks joined if they intersected in 0 points. And then there's a theorem of Hotels and Seidel that says that such a graph is strongly regular, and you prove that with a little bit of matrix theory, which is outlined here. You take the incidence matrix of the design, so rows indexed by points, columns by blocks, and you put a 1 if the point lies in the block. Then MM transpose turns out to be a linear combination of I and J. M transpose M is a linear combination of I, J, and the adjacency matrix of the graph. And from linear algebra, we know that MM transpose and M transpose M have the same eigenvalues, the same multiplicities, apart from possibly the eigenvalue 0. And using that, you can calculate the eigenvalues of the adjacency matrix of the graph and show that it's strongly regular. And I would just like to finish up with one more graph because it's not a triangle-free strongly regular graph, but as far as I'm aware, it's the only strongly regular graph that actually has my name attached to it. So it's built from the VIT Steiner system, the Steiner system on 22 points. So this is what we do. Instead of the sort of constructions we did before, the vertices are all the 2-element subsets of the 22 points. So there are 22 choose 2 is 231 of them. And we join vertices A, B, and C, D if those 2 sets are disjoint, but contained in a block of the Steiner system. And that turns out to be a strongly regular graph, and there are its parameters. So with that, I think I will conclude. There are plenty of problems there for you to tackle. As I said, I didn't think we could probably solve them in real time, but you can take them away. And if you want to see my solutions, just email me and ask, and I'll send you a copy. So that's it. Thank you very much for your attention.